Okay, I think we can start. And yeah, I think so. Today, Gora is going to talk about like how to simulate like deep neural networks. Because Gora actually has done maybe the first project in our group about deep learning. Particularly, we found something quite interesting in terms of like this sort of fractional diffusive dynamics of deep learning. And but we also want to carry on along this line of research. There are a few ideas we can pursue in the future, such as we can introduce the attention mechanism we found from our biologically realistic circuits to deep neural networks. And also we are interested in developing a new learning algorithm. I mean, that's a project Kevin has been working on. So I think in the future, more or less, we are going to work on this interface between, of course, physics, computer science, and also machine learning, AI, and computational theoretical neuroscience. So that's another line of research we are going to stick to in the future. But anyway, Gora is going to tell more about how to simulate these sort of networks. Actually, Gora is leaving on Sunday, right? But
yes.
Yeah, I heard that you guys had a very big party a few months ago, right?
Yes.
And I saw going on in person a few days ago. We had a lunch, but unfortunately, because of this current virus situation, we can't have a big group lunch. And but anyway, we wish all the best to Guodong.
Thank you.
And Guodong, I mean, now is applying for some international postdoc positions, and he has got some sort of interesting verbal offer, right? Heading to grants availability in some famous and big research groups in the US and in Europe. I think he has very good opportunity there to secure some jobs in some big groups. But anyway, I think in the future we are going to have this sort of like group meetings. We will keep Gordon informed. So Gordon, you still can feel free to attend these sort of like seminars or journal clubs.
Good.
Yeah, I think next time Yishi may present some papers of working memory. Is that okay for you, Yishi?
Okay, no problem.
Yeah, maybe next week. Yeah, next week you can talk about different models of working memory and also some psychophysics studies about the working memory, because Yishi has been working on developing a new model for unify different theories of working memory, and it's quite interesting. So next Friday maybe.
Okay.
Yeah, Gordon may be able to attend it remotely somewhere in Shanghai or in Beijing.
Yeah.
Okay. Anyway, so let's start now.
Okay. Thank you for the introduction. Today I mainly will talk about the Python library, Pytorch. Pytorch now is a very famous library for simulating deep learning, especially compared with TensorFlow, which is developed by Google, and Pytorch is developed by Facebook. Now you can see in this diagram in NIPS, at least in the NIPS conference, more and more papers are using Pytorch instead of TensorFlow, because Pytorch has a very slow flight learning curve rather than a steep learning curve like TensorFlow. TensorFlow is like they invented a new language rather than Python itself. It's a bit flexible, but hard to learn and hard to use. But the speed is quicker than Pytorch. So I highly recommend you guys try Pytorch, because if you can use MATLAB, then probably you can use Pytorch. Okay. Then first, I will discuss how to install Pytorch, and then some basic syntax of Pytorch. Then I will discuss the core part of Pytorch, is the autograd, which is doing backpropagation. And then I will use a very simple model, introduce how to build a neural network and train a neural network. And then finally, I may, if I have time, I may introduce something I did in the third project on my PhD. Okay, let's start from the installing the Pytorch. So first, you have to install Anaconda. Anaconda is a very useful integrated environment for Python. It can control, like install, upgrade, uninstall also Python libraries like NumPy, SciPy, PyTorch, and TensorFlow. First, you install this, and then you can go to like prompt and Conda prompt. It's like something like a terminal, but you can run it in Windows. So it's pretty good. And then you just Google PyTorch. In the PyTorch official website, you switch to get started. Then you can choose which version you want to use and what OS you have. And then you choose package. Since we installed Conda, Conda is one of the Conda. Then we choose Conda. And you can also use pep, which is another popular way to install libraries. And then we choose Python or C++, and based on the CUDA version. Or you don't, if you don't have CUDA, you only use a CPU only. Then you just copy these commands to your Anaconda prompt here, and then everything will be done automatically. You don't worry about that. If you are in a Linux system, that's even better. Normally all Linux has integrated pep. Then you just choose pep and copy this command to your Linux terminal. Then that's done. Pretty neat. Okay. See what's next. Next is a basic syntax of Pytorch. Once you have downloaded Anaconda, it integrated the Jupyter Notebook. Jupyter Notebook is a very useful tool to like demonstrate your code and also debug your code. Once you run the Jupyter Notebook like this, Jupyter Notebook, and we'll open your this, like I'm using Chrome, so it will pump out this page, and then you can run some Python commands here. Like here in each block, you just type your code here, like import torch. Torch is represents PyTorch. Torch is Torch is actually an even older Python library for simulating deep learning. PyTorch is a Python like Python version Torch, so it's called PyTorch. So still we use Torch as a name for the library, and we run this block, this cell, and then we can try to set up our first PyTorch variable. So in Python, everything is a class. So it's object-oriented programming. It's different from MATLAB or C. So this torch is like a class. It integrated lots of methods and variables inside. So if we, for example, we build a matrix, which is 2 by 2, and all the entries are 1, then we just type this, and we can print X. And then we can run this cell. Somehow my computer is very slow. Let's have a look. 1 sec. Oh, this is weird. Let me try again. try this again. Import. I don't know this. Okay, now it works. So now we have we print this x. X you can see, as you can see here, is 1, 1, 1. It's a 2 by 2 or 1 matrix. So similar syntax as MATLAB. Instead of you have to add this pre-term here, it's torch. And for example, you give like x equals torch or ran and 2 by 2 and print x. Okay, this is a random matrix drawn from uniform distribution. So things like this. If you want to know more about the torch, you can go to the documentation of the Pytorch, and here you can search anything you want. For example, the function we just used once, and you can see what's the arguments like size or data. Lots of attributes you can cite, like the tab of the data and which device on CPU or GPU. Because now in my local computer, I don't have a GPU at the moment, so I only use CPU. Okay, this is how to set up some tensors. And then I will talk about, let's see, yeah, some operations. Yeah, operation, class, object, okay. For example, I would like to add, build another rand, and we plus, it's just basic, exactly the same with MATLAB. Instead, they may, for example, like print the, okay, this is plus and also minus, times, and also division. But to be careful is because for the power, in MATLAB, it's maybe you are familiar with this, but in Python you use this one, the letter, to represent the power. That's the only difference, I guess. Okay, that's some basic operation, and also you can use some comments to calculate. For example, I have y, and then I use y dot add. Add is like, because y is a tensor. This tensor is a class. The class has some built-in method. So add is one of its method. To add something. For example, I add x here. So it equals to y equals y plus x. Okay. And another a bit unique operation is called in place operation, which means if you add underscore, basically every function has this in place operation. You add an underscore after the function name, and then it will change the variable in the memory directly. So instead of calling a y, it will change the exactly same memory location, change that value. So this should be very careful when you use this, because in Pytorch, basically everything you have written is needed. The autograd means you have to calculate the gradient based on the backpropagation. But if you use the in place, it means no clone. It just change the memory. Then you can't use the backpropagation. So that means the in place operation will cut down the chain rule graph. So to be very careful when you use this. That's a basic syntax. I think it's enough. Other things is just like change the reshape. In Pytorch, it's called a view, similar to NumPy. I can change it to other shape. Yeah, like this. I changed it from a two from a 2 by 2 matrix to 4 by 1. -1 here is just like in MATLAB you do reshape, like keep the first dimension as 1, and then you use this to represent the arbitrary dimension based on your input matrix. Okay, I think it's basically enough for the syntax. It's very easy. Next point is, let me check this. Yeah, NumPy transfers. Because in Pytorch, everything it is represented as a tensor. Tensor is a matrix, but this tensor is different from the NumPy's data structure. If you would like to use some NumPy operation, NumPy function, you have to transfer the tensor to a NumPy matrix or NumPy array. The syntax should be like this: torch from NumPy. Oh, sorry, this is, I should give to, let me think. Oh, yeah. Y dot NumPy. Yeah, because NumPy here is a built-in method in this Y class, this tensor class. Y is a class. So then if we print B, the B become a NumPy array now. Okay, then I import NumPy. Then I will tell you how to convert a NumPy array to Python to Pytorch tensor. Okay. And you will have a C equals torch from NumPy. B now is a NumPy array, so I transfer it to. Okay, now we print C. C becomes a tensor again. So this is how you bridge the NumPy and the Pytorch, because some Python NumPy functions are very helpful and useful. You probably have to switch between these two things. But remember, if you are in GPU computing, converting to NumPy means you will first copy your variable from GPU to CPU, and then you come back from CPU to GPU. This will be a bottleneck of your code, will make your code significantly slow. So be careful when you use this. Okay, then let's go to, yeah, I will give you 2 websites. These 2 websites can help you learn further. One is like the documentation I mentioned. You can see lots of, Pytorch API here. The most useful thing is first is the tensor. You can see what the tensor data type can be and what's the built-in method. Like I use the NumPy, IDE, those built-in methods. Another useful API is Torch NN. Let me search it. Torch.nn. Yeah, it basically contains everything you need in deep neural network, like pooling layers, padding layers, convolution layers, other activation functions, normalization, dropout. So everything is already programmed. You just have to call this function. This is how you use the documentation. And another thing is the Pytorch forum. This is a place you can discuss and ask questions here. I used to ask lots of questions here and answer lots of questions. Basically, everything you need for beginners, you can find here. You can find everything here. Okay. So good, next step. we'll introduce the back propagation or the autograd in Pytorch. Okay, first we should understand if you attended my last presentation about deep learning, you probably remember what is back propagation. It's just a chain rule. So in Pytorch, we will first create a cyclic graph. It's a graph you can think. Let me draw a small picture here. For example, G X. So if this is X, this G X, then this becomes this. So it becomes a graph. No cycle. So it's called a cyclic graph. So we first build a graph. It can be really complicated. For example, for multiple variable, it may have some branch somewhere goes here, like this, where it can be very, very long as well. And then we, based on this graph, calculate the gradient. This is a very powerful autograd tool. So I will introduce now. That's it. Let me hide this. First, I would see, yeah, one more syntax is related, also related to the autograd. Is when you build up a tensor, you can specify the an attribute called the requires grad to true. That means this tensor need to calculate the gradient later. Let's see. So then it has the attribute here. In default, requires grad equals false, means this is only a tensor. You don't have to calculate the gradient. When you really need a gradient calculation, you have to specify at the leaf. Like you remember the figure we just draw, the x here, and then gx, fx. The x is a leaf on the graph. So that this leaf node should be specified. The attribute of a requires grad of this leaf node should be specified as true. And then the following variable like this, y equals 2 times x, since x is will inherit the attribute from the leaf node. For example, the y now, the y's requires grad. This attribute is also true, although I didn't specify it. So, any questions here at the moment? Okay. Then let me see. We can set up a bit complex here. For example, x2 2 and plus 2x and plus a constant. This is y, and then I probably will. And yeah, let me see. Yeah, and that's y, and then I will calculate dx over dy over dx, which is the gradient. What I do is y out backward. So this is just an example. It's only for dy dx. Actually, you can use another variable like z equals to fy. Then it become a chain rule. So for simplicity, I just use one function here, not a nested function. Out backward. Okay. This will calculate the Jacobian matrix. But for Pytorch, if your function's output is a vector instead of a scalar, you have to give a vector in this argument. For example, now I want to it output the original Jacobian matrix, and then we just give a vector here, 2 by 2, because the x is 2 by 2. Okay. So this actually is calculating the vector Jacobian product. Sorry, no out here, only backward. Print. Then I print the gradient of y respect to x, because y could be a multivariable function. So you have to use a leaf node attribute grad to output the y's gradient with respect to x. Okay. What? Let me double check. Oh, okay. Yeah. I have to set. Because the gradient is accumulated, is accumulating. We probably have to clear it first. No? Sorry for confusing you. Okay, because it's like the reason is when I calculate the y's gradient, then y is kind of kick out from the graph. So when you actually want to calculate the gradient again, y actually is not in the graph. So you have to delete the y and then reset up the y variable and then recalculate this thing. Then it can output the gradient, which is this. This is how we calculate the gradient in Pytorch. So any questions so far?
Yeah, I have a question.
Yeah.
Yeah. Just to ask here, the first is the graph. Like, what does the graph mean? Like, I saw your drawing, but what does that mean? Like, is that a flow of the calculations or?
For example, this is a nested function, right?
Right. Yeah.
So when you calculate the dy dot dx, what will you do?
Or just take the derivative of the function, right? Like the.
So first you calculate for this, right?
Yeah, that's right. And then you do the one inside it. Yeah.
Yeah. Sorry, this gx and this gx.
Yeah, that's right. The chain rule. Yeah.
Yeah, chain rule. Then I just put this chain rule as a graph.
Ah. Okay.
With x, and then I calculated the dy dot dx. Okay, and then dx. Something like this. Does that make sense?
Yeah. Is it like telling the computer, say, you need to calculate in this sequence and like that, or it's like instead of
The
equation?
graph is a data structure.
Ah, okay.
Yeah,
Yep.
yeah, it's a data structure to save this kind of chain rule, because sometimes this chain rule could be really complex. It's not this explicit, especially when there are millions of variables. You have to calculate the partial derivative based on the chain rule. If you have the graph, for example, is multi-variable, I can follow follow this line, or this line, or even this line.
Ah, okay.
Yeah.
So for visualization of the variables and calculations.
It's not for visualization. It's just for the computer to look for the root to calculate the partial derivative.
Oh, okay. Got it. Yeah.
Yeah.
Yeah, clear. Thanks.
No worries. Any other questions? Because I made some mistakes here, may confuse you. Is this part clear to you?
Guozhang, just one question. So in line 24 and 25, like when I happen to rerun it, 25 produces a different result. So like, do you mind doing that? If you rerun 24 and 25?
Yeah.
Like every time you do that, it accumulates, right? So like,
Yeah, it's cumulative.
yeah, and how do you like reset it to 0? Is it?
Oh, it's give me a sec.
Sure.
Let me. I remember it's 0 grad something, but I tried it, but it was wrong. It's a bit weird. Oh yeah. Let's have a look.
I think the moment when you reset X, it resets Y.
Sorry. Dan, what did you say?
When you redefine X or reset or rerun the cell with X in it, where you define it as torch.ones, when you redefine that, it resets X. Oh, sorry, resets Y back to 0. So if you rerun cell 15, which is redefining X.
Yeah.
And then every subsequent cell.
Yeah, you're right. That's I know this way. It's just like a reset the X. That means you set up a new graph. When you give a new leaf node, that means a new graph, because leaf node is a starting point of this graph. So you give a new graph, then it will give you a new gradient. But if you still following on this graph, it will accumulating the gradient. Kevin's question is what a function to reset the gradient. But I currently I don't know for this simple case how do we reset it. But I know for a module like a neural network, we can use this zero grad to set gradients to all model parameters to 0. For this simple case, actually I don't know what's the function for this specific type, for this specific tensor. I don't know.
Oh, it's okay. Don't worry about it.
Okay.
Yeah, we'll just move on. I guess it's fine.
In the module part, I will mention that. Okay. Okay, and then detach. This is a very useful stuff. For example, you are in a graph. In the middle of the graph, you would like to get a variable from the intermediate node of the graph. But you don't want any gradient here. You do white detach. That will give you a, let me see. Yeah, give you a tensor. The value of the tensor is exactly the same with y, but it doesn't have the true attribute of requires grad. That means it's kind of detached from the graph. Did I express myself clearly here? I better draw a picture here. So this is a graph. So I want to know this value, this node's value. So I do detach. And I can calculate for the following, calculate lots of operations based on this y dot detach. The value is exactly the same, but it won't influence the graph. Because if you, for example, you calculating this, for example, you calculate z equals to y times 2 here, and z requires so this will give you a variable in the graph, so it requires gradient. If you use a detach, is C1. Times 2. And it's false. So I think it's clear. So it's you use another variable outside of the graph. This is how you build a new variable in the graph. So extend the graph. Okay. It's pretty useful. When you don't want to auto-grad something, you use detach. Always remember this. Otherwise, your derivative graph is changed. Okay. Then let's build a very simple neural network. Okay. So as you know, Python is an object-oriented programming language. So everything will be programmed in a class. So we first import a few useful libraries in Torch, and then we build a class of a neural network. For the documentation of these functions or these libraries, you can check the documentation for details. So this NN that I mentioned, the neural network mode API in Torch. This is a sub-module under NN, which is called function. It's lots of useful functions like ReLU, soft marks, sigmoid, things like this. Okay. And then we build a class. So net and module. This means I inherit the class n.module. So the n.module is a built-in class. It's for like the basic infrastructure of a neural network. You inherit it. It contains many built-in methods as well. For more details, you have to check the documentation. And then we define the initial function in the class. Could be this. The initial normally will claim or set up some variables. For example, I will build maybe 2-layer convolutional neural network, and then following by 3 fully connected layers. So I will use self.conv1 is just a variable name, and then nn.convolution 2D is a 2D convolution layer. And here I will use one channel, and it has the input channel is 1, the output channel is 6. Let me show you this documentation. you see this is the function, and all the parameter here is first is in channel, input channel, number of channel of the input image. Channel means, for example, if it's a grayscale image, then the channel is 1. If it's a RGB image, then the channel number of channels is 3. So that's the channels mean. And the number of channel produced by the convolution is an output channel. It can be arbitrary based on your network structure. So, and this is the kernel size. Basically, we need the first 3 arguments. That's enough. For the rest of this a bit advanced, it's not covered in today's tutorial. Okay, we will use the first 3 arguments. The others, the rest are optional. Do you have any question here in terms of this function? Okay.
Yeah, I have another question.
Yeah.
Sorry. Yeah, just asking. So this function, you know, the module, the predefined functions are already built in, so it has already a like basic structure of neural network. You just used its framework to actually develop your own, like modifying its structure to do your own like the neural network, right?
Yeah.
Okay, cool. Thanks.
Yeah, of course. In documentation, base class for all neural network modules. Yeah, you can read all. There are lots of built-in methods in this base class. I want to cover them in today's tutorial because it's just for simple tutorial, not advanced level. Okay. And then I use the next define the next convolution layer, n dot convolution 2D. So because this guy output this number are arbitrary, I just give you an example here. So the first layer's output channel number is 6. So the next layer's input channel is 6, right? And then I use a 16 channel for the output. The kernel size is still 3. 3 means 3 by 3 in the convolution kernel is 3 by 3. And then I will add a few fully connected layers. Then dot linear. Let me double check this. Because the syntax are really complex. Nobody can really remember everything. So when you use these functions, you'd better check it. The size of input samples. Out feature means size of each output samples. Bias. Okay, bias is B. Fully connected. Okay, clear now. Okay. 16 channel. Yes. Let's imagine the matrix, the image is a gray image, and it's the size of the image is 6 by 6 for simplistic case. 6 by 6. Okay. And then output 120. It's all arbitrary. It's all arbitrary. So just an example here. Okay. It's a purely feed-forward neural network. Okay, next here. For example, our class number, the number of class is 10. So let's label here. Class is 10. Okay. And the input image is 6 by 6. Okay. Then the last fully connected layer should be the output size of the last layer should be equal to the number of classes you are classifying. Is that clear? It's for example, you have 10 kinds of dogs and you want to classify them, then you have 10 classes. Then for the final output size, you also should output 10 variables. Each variable represents one kind of dog. Is that clear? You give me some response. Is that clear?
Yeah, clear.
Yes.
Okay, sure. Some people use a softmax to normalize the last layer. Okay, we'll go through that later. So this is a definition, and so I'm not so good at Python. So normally here I saw some people's example code. They often add this. So I'm not so sure what's the function of this guy. Or I just add here. So probably result is still can work. I'm not so sure.
Shencong is a Python expert.
Yeah.
Shencong, what do you think about that line of command? Shencong?
Yeah, sorry, I don't know that.
Oh, you don't know that. Okay.
I googled that before. It's like kind of borrow the what I don't remember. Sorry, borrow the self variable
Okay.
class or something. I don't remember actually, and it depends on the Python version as well. If your Python is advanced, the version is advanced, probably don't have to use this. Not so important. Doesn't have so much meaning. And then we go to the forward. Forward is the main function actually in this class. Means how you construct your network. Now we just define some layers. Now we connect those layers together in the forward function. And this forward and init, this function's name are keywords. Means you must use these words. Otherwise, the Pytorch cannot work. Okay, and then okay, x is our input, the image. Okay. Let me think. Yeah. We first puts the x, that our input, the image, to the first layer of the convolution neural network, and then we add a ReLU layer, the activation function, after this convolution layer. Okay, and then we add a max pooling 2D. I will explain it, or it's max pooling. So max pooling is like, let me draw a small picture here. See, this is a matrix. Probably draw a little bit bigger. And has lots of values, right? Then I want to cost-greenize this matrix. For example, now this 4 by 4. I want to change it to a 2 by 2 matrix. Then I will first consider this part, this 2 by 2 part of the matrix. In this 4 entries, I choose the max value as the first value here. And then for this part, for this 2 by 2 sub matrix, I choose the maximum value That's this one. And then for this, give it here. For this, give it here. So this is called mask pooling. Okay, then this is the syntax argument we need. Input weight. This is, oh, sorry. It's not. Okay, this is max pooling arguments. Max. Let me check. Okay, save the window to take. Yeah. Okay, that's clear now. We give that kernel. We choose every 2 by 2 submatrix, the maximum value to the next co-screened matrix. Okay. And this will be our new X. And then we keep going. Put the second, use the second layer and repeat it again. Value. Go to the. You do it again. This time I use 2 because it will become this. Okay. It's just another layer. Okay. And then I will reshape the X a bit. View is, remember -1 represents the arbitrary dimension. Yeah, 1 sec. Let me check. 16 should be okay. Yeah, let's add another. Let's add another function after this later. Okay. Just leave it here, and then we do next. I will go back to this step later. Okay. Then we go through those fully connected layer. And then for the final one, so FC 3 X return X. Yes. So forget about this first, and then for the rest, do you have any questions so far?
Yeah, about the f dot relu, what is that? What the function there?
Sorry.
What is the function of f relu language? You know, the one
Value.
for the, yeah.
Value is a regularized linear unit. It means this X is 1. And this function is just like you get rid of all values less than 0, and then keeps the positive value as the same. That's called a regularized linear unit. Most of people call it a value.
Okay. Yeah.
Yeah. It's to introduce some non-linear operation here. Because if you directly input the upper layer's output to the next layer, then it becomes a purely linear operation. You know, linear operation is not so sophisticated. If you would like to, you know, deep learning is actually like a adaptive basis regression or curve fitting. So the bases are adaptive. So it's like a curve fitting. If you want to fit a very complex function, you must need a nonlinear operation fit it. A simple case you can imagine is like a Taylor expansion or Fourier transform. If you like to face a complex function, you need those nonlinear terms. It's like x plus x squared plus x cube. This is linear, and this is nonlinear terms. It just give you an equation.
Okay. All right. Thanks.
Nice.
Sorry, Guojong. For the initialization, should self FC3 that line should it be 80 in 10?
Oh yeah. Great. Thank you for that. Yeah.
Sorry, another typo is on the ReLU. I think the ReLU function, the bracket, it should be, I mean, the second ReLU function, the bracket should be, yeah.
Oh, yeah.
After, yeah.
Yeah, good point. Thank you. Nice. Okay, and then since I have to reshape this, because after the convolution, the output is a matrix. I have to put this matrix as a vector, as a one-dimensional vector, and then feed it to the fully connected layers. So I have first calculate the number of entries, number of flight features. Okay. Use another function to serve this line. Okay, so size is just like MATLAB size, but this is a built-in method, so it's not size parenthesis x, it's x dot size parenthesis. So basically, if you know MATLAB, you probably you can know everything here. Not so difficult. So features. I need a one dimension. So don't worry about this part. This part is not this part is not so relevant for our today's tutorial. Just normal thing. Then I can -1. So okay, don't worry about that. It's just this line is just to reshape a matrix to a one-dimensional vector. Okay, don't worry about this detail. Let's move on. So then that's our class. The class is done. Okay, right. Okay, good. So the class is like you define a new data type. This is a new data type, and this data type contains this built-in methods inside. So I will use this data type to set up a new variable called net with lowercase. This is the convention. Use the uppercase to represent the data type and the class, and use the lowercase where to represent the variable. Okay, and we print net. See what is the net. So it tell us its convolution. What's the convolutions convolution layers parameters. Okay. Okay. And any questions so far? And then we can output the parameters of this network. Parameters, because you remember this net inherit this base class nn dot module. So this nn dot module contains many built-in methods. This parameters is one of the built-in methods which can give you all the parameters in this neural network. And then let's print, see what is the parameter. So these are parameter containing, because if you set up this, in default, it will be a Gaussian noise. Every parameter is drawn from a Gaussian distribution, standard Gaussian distribution. Okay. Okay, let's move on. Yeah, next we go to we set all the gradient to zero the gradient, and then we can calculate a password. Remember our output, the output size is 10 by 1 by 10. So I times the 1 by 10 vectors here to calculate the vector Jacobian product. That means to just give you the original gradient. Oh, yeah, alt, yeah, alt. Sorry, I have to give input first. Give input first. The input we give a random variable here. It's not input, it's intermediate. Input, let's give input a bit larger. So the C14 has the image size 32 by 32. Let's use this. Let's give a random number and then run it. Still, let me check what's the difference before. Oh, okay.
Oh, you missed an S somewhere, I think.
Sorry?
You missed an S for S in size. Num feature, you're missing an S in that function. It's just a typo. For S in size, so define num flat features, that function.
Yeah.
In the for loop.
Oh.
You're missing an S there, yeah.
Okay. I see. Okay, good. Then it did one step of autograd means calculate the chain rule once. Then we can this is just a simple like example. So for a real neural network, we have to define the loss function, but we can't use this kind of thing. I just give you an example. You get the meaning. Okay, and then we criteria give a loss function here, MSE loss. Let's use MSE loss, and let's check it. MSE loss documentation. No. So we basically don't have to give any arguments. So because we are using a default setting, okay, then that's a loss function. It's done. It's criteria, and then we get the loss function criteria. So it will generate another. It's like a function. The criteria now is a function, and then you give the output and output of the network here. This output, and target. We should come up with some target here. Target. Since it's 10, 1 by 10, and we give a random 1 by 10, and make sure the shape is the same, 1 by 10. And then there is a loss. That's print loss function. Okay. And then see the gradient function is MIC loss backward. That's good. Then we have to run the back propagation. Then now this is back propagation, just as I mentioned 1 minute ago. First set every gradient at 0, and then we do 1 back propagation backward. So, oh, sorry, 0. Okay. So now let's print one of the network's parameters gradient. Let's print the best. Okay. So it's calculated because we have set it to 0 before, and then we calculate once, it generates a new gradient. No, it's a new gradient. Okay. Then we have to update the weights. Any questions so far?
Hey guys, feel free to ask questions. Guoran is working really hard and trying to go through the whole thing. I know it's challenging to do this sort of real-time coding stuff. Any questions, Shensuan?
Yeah. Sorry, I have a stupid question. Like in cell 54, how did you end up with the 13232? How did you get that number? Those numbers.
It's like I said, it's an arbitrary number. It's an arbitrary number because the CIFAR 10 image, the size of CIFAR 10 image is 32 by 32. I just use this arbitrary number.
As in like how do the numbers match up with the input defined in the classnet? The dimensions.
We didn't specify the input size. We only give the channel. The channel is 1, and that's good. Only need the channel. In Pytorch, normally we use NCHM. And let me give you that documentation now. It's a good question. It's a good question, not a stupid question. I missed this part. See, this NCHW means when you give input to the convolutional neural network, you always give in this kind of format. N is a number of image, and Cin is a number of the image channel. For colorful image, it's 3. For grayscale, is 1. And maybe for other data type, you can have even more channels. And H is the heat, W is the width. So in convolutional neural network layer here, we only need to give input channel and output channel and kernel size. We don't have to give the H and W. So these two variables are arbitrary based on your data. Is that
right?
Clear?
Right, got it. Thanks.
Oh,
I have a question about the loss function.
yeah, go ahead.
Yeah, so from there you define the criteria as the loss function. So that's also a building function. And so can you define it like you change the functions you wanted, or it just has to be like the same as the defined one?
Oh, you can define it anytime you want. It's like let me try to. Oh, this. Say loss function. I will choose loss function. There are many choices for you, and you also can define it by yourself. You remember that? Right. All right. I'll give you some advanced tutorial now. This is
Thanks.
like the class here. You inherit the end-of module. Right. So, for example, you would like to build your own class function. Then you do this loss function and dot mse loss. It will inherit most of the built-in function, but you can define your own here. Define still initial, and then define forward. You can check the source code here. This see this how they build, still like this.
Oh.
Yeah, like what I said, but the keyword is a bit different.
Yeah.
Okay.
So we can check it and modify if we want to.
Yeah.
Yeah.
It's very flexible.
Nice.
But normally we just use the default one because there are many choices and also regularization terms after that. Many options here. Okay.
Yeah.
Hi, Guozhang.
Yeah.
I have a question about the number of channels in the second convolution 2D. The second.
Yeah. Go ahead. Yeah.
Yeah. Why is it 16?
All these are, like I said, arbitrary.
Sorry. Why is it 6?
Arbitrary. Still arbitrary.
But you say for the color image, the channel is 3.
This is the input channel. This is output channel. So input is 1, output is 6. The channel, when you input the image, the channel number depends on the data you are using.
Okay.
Yeah. After the first processing layer, then it's arbitrary. It depends on your mind or your experience. I don't know. I just gave an arbitrary number here.
Okay. Thank you.
No worries.
Another question is that when you define the loss function,
yeah.
No, the last line, I think. Move. No, not this one. The loss function.
Yeah.
You say when you define it, does it automatically add to the network?
No. The loss function has nothing to do with network. Network is network. Network only generates this output, and then the loss function calculates the loss between output and the target.
Okay.
Yeah. It's not linked to the network. It's totally separated.
Okay, thank you.
No worries. Then let's update. Let's update the weights. Update weights. Let's give you some more detail here. Let's see. If you still remember, I told you last time that W new, W is a weight, W new equals to W old minus learning rate times gradient. That's a famous gradient descent method. So what we do here now is just follow that math formula. We do not parameter. So this means I get every parameters in the network loop among all those parameters, and then we do for f dot data. You have to check the documentation for all these attributes. So subtract. Okay. Let's use in place because we don't need the auto grad here. F grad dot data times learning rate. This is a gradient. Get the gradient's data. in the value and times the learning rate. And then because this is the original weights, and then I minus the gradient plus times the learning rate as a new parameter. Is that clear, this part? Gradient descent, very simple, right? Okay. But what if we want to use some advanced learning algorithm, like Adam and this stuff? We normally won't write something like this. We use another class, optimizer. Let's first import it. Import torch. Give the, let's have a look. What is SGD syntax? I don't remember most of them. Every time I have to check it to make sure it's correct. So okay, the parameter, learning rate, moment. Okay, the rest of the part I won't go through it today. You can read it by yourself. Okay, only the parameters here. The parameter and the learning rate. Okay. This is our optimizer. And then we have to set the gradient as 0. It's kind of like a small bug, I think, in Pytorch. Every time you have to set it to 0. I don't know why they don't automatically do this. And then we optimize. To make it the whole thing together, I copy those things here and optimizer dot step. That means I will calculate the gradient here of the loss function, and then I update the parameter for one step. Then, for example, I have a 10 epoch. Then in every epoch, I choose a mini batch. See that if there is a train loader or something here. And then we will do output. Filtering loss, the loss here. Okay, then that's a neural network. I won't run this because I didn't load data now. Also, it's like in every epoch and in every mini batch, we calculate the output from neural network, and then we calculate the loss, and we calculate the gradient of loss, and then we update the weights, and it's done. Then this it is a neural network, and it's how we train neural network. Any questions? So very simple. I think it's only need this is how many lines? 1, 2, 3, 4, 8. Less than 10. This is at most 30 lines. You can build up convolutional neural networks.
So question, what is train loader?
Train loader, well, I just show here as an example. For example, it could be a dictionary or something like that. Pytorch has a built-in function for train loader. I remember train loader. Now this. Let me think about. See this kind of thing. We can write build another import. This is Torch. This is Torch Vision. This is another library. Torch Vision contains some common or ordinary training data set. Let's see, Torch. Sometimes we need to augment, transform the data set, like add some noise, and we shift the data for well, and sometimes we need the transform. And then we use this save button. Root is just the path. The path, for example, like data or something like that. And then this will be the train order.
Yeah. Okay.
The data structure is like a dictionary, like the one label, one image, one label, one image. Yeah. But I won't download it here. It's a bit huge.
Okay.
Yeah. Probably I have to make this more explicit. Like yeah, that's it. That's all how you train on your network and how you build on your network. Our tutorial is almost finished today. Have any questions?
Yeah. Actually, about the epoch and the input. So you have 2 for loops, and so are they like the structure from the train loader?
Well, I don't understand your question. Sorry.
So for epoch in range 10, so what does that mean? Like you have a for loop in here.
That means you run your gradient descent 10 times, and in each time you update the weights among all data sets. So epoch means how many times you update the weights.
That's okay. And then what about input in train loader? So it's like that's defining so where you want to get the data from, like the input in the train loader. Does that mean that?
Can you repeat your question?
Okay. So the for input in train loader, so train loader will know that now is the data, like the way the data structure is, and then for input, so that's the one we want to like extract it, right? Is the data from the train loader?
Yeah. That's a syntax of the for loop in Python. Yeah.
Ah, okay. All right. Yeah. Thanks.
No worries. So for example, I still putting that cheat sheet of Python. Maybe you haven't go through that. For example, is if A is a list. A, B, C. Range. When I sorry. When okay, that's it. So it's not like MATLAB. MATLAB only can use scalar. It can use any data structure. The for loop can use any data structure, either array, dictionary, or even other class like a numerator, things like those.
Yeah.
Okay. No more questions for this part. Then I will quickly go through the third project, maybe in 5 minutes. It's my GitHub. currently it's not anonymous for NIPS review, but you can still tap the address in your browser and go to my website. For the first one is anomalous diffusion dynamics of SGD. And once you get in here, I have wrote a markdown documentation here, how you install all the requirements, how you train your network, how you calculate the eigenvalue of Hessian matrix. Yeah, everything you need is here. Even the PBS script is saved, is stored in this repo. And the structure is what we just learned is in here: train model and models, ResNet, XNet, SysNet, and VGG. Lots of different network structures. And here is just basic class, the innate forward, what's the layer, and what is shortcut. If you understand what I just shared with you, you probably can easily pick up all this advanced programming. It's just a nested class. One class use another class, maybe a full nested class together. And then we'll make like a make layer or something like this, and then make layer together, things like. So the idea is the same, just more variables, more layers, and more structures. Yeah, that's it. I hope you enjoy this tutorial. Thank you.
Okay, all right. Any questions, guys? So this is Guaran's GitHub, right?
Yeah.
Yeah, so in the future, maybe some of you may work on these sort of projects. So we can ask Guaran to give you rights so you can access this GitHub.
Oh, it's public. It's published.
Oh, it's public. Oh, yeah, because it's for review purpose. So you guys can access these